So today we're going to keep talking about capacitors and how they work. And so today we're going to keep talking about capacitors and how they work. And so what they are, just to remind us from yesterday, is that they're two metal plates and they get a charge. Well, how do you charge them? You have to hook them up to a battery. In this case, they have it to a 12-volt battery. That's a very strong battery. That's a car battery. And we said also that often what they'll do is they'll roll them up. So I drew a rough picture in the last video, but you can see there's two metal plates. They're rolled up, and that yellow in between them is an insulator, or what we call a dielectric. Just so we're using the terminology early. And you'll see here, most of these capacitors over here, like I know I have this kind, especially for using in the lab, they look like a can. Or you might see smaller ones if you've ever taken something electronic or electrical apart, and you might see those kind of capacitors. Sometimes they call these a button capacitor, where they're a little rectangle or a little circle, and you can see they kind of look like a little button of sorts. Well, let's get into what is the capacitance. And the thing to remember is Q is delta V times C. Or the easy way to remember it is QVC, like the shopping channel. So Q is the charge that gets stored on these plates. C is what we call the capacitance. And capacitance is measured in farads. I said it wrong because it's named for Michael Faraday, who was a very important scientist, chemistry and physics in the 1800s. So it's named for Michael Faraday. And the V is the voltage, if you'd hook this up to a battery. We'll just draw a car battery here. Now, most capacitors, the farads, their numbers are pretty small. They're between like -12, which is a picofarad, to a microfarad, -6. So the numbers you're going to see on capacitance are really small. You say, well, what is it? Really, capacitance is a way to say, how much charge can we store on this plate? It's a good measurement of how strong the capacitor is. Now, another way to calculate it, if you don't know the voltage, is we can actually calculate it just from the size of the plates and their spacing. So if we have two plates, I'm trying to draw them somewhat three-dimensionally, well, they'll have a certain area. Now, you don't need the area of both sides, just the area one is fine. You don't have to double it. And the distance. So C is that funny E sub 0, and I'm even going to jot it down so that I don't forget it, 8.85 times 10 to the minus 12, because that's not a number that we use every day like pi. The distance is the spacing between them. Now you see distances in the bottom. The closer you can get these plates, the higher their capacitance. Area is in the top, in the numerator. The larger the area, the more capacitance. Just like, again, we use the idea of aluminum foil. Well, if you have a really big piece of aluminum foil, you can put a whole lot more charge on it. If you can decrease the distance, you're also going to increase your capacitance. The closer together you can get them, the better. And I'm going to show you a nice little tutorial thing online in a couple seconds here. So how does this work? While you're charging a capacitor, capacitors don't charge instantly. If you've ever used the flash in a camera, it has like a certain refresh rate. You can use the flash, but usually you can't use it immediately right afterwards. It has to charge back up. You might say, well, how about when you see, on TV where the flash bulbs are going at a sporting event or a celebrity thing or even a political thing? They carry like these really big capacitor packs with them. But for the average camera on a cell phone or a digital camera, you need to wait a second or two before it charges back up. So while it's charging, ions are flowing in the battery. We don't care so much about that part of the chemistry right now. But I think you can see that we're starting to build up charge, positive on one plate, negative on the other. And in case you didn't know this, this is kind of interesting. The little cap on the battery, the little bump at the top, that's always the positive end of the battery, and the negative is the flat end of a battery, whether it's a AAA or AA. Now, at a certain point, you can't put any more charge. You've got the maximum charge possible on each plate. They can only take so much. There's only so much space, basically, that they can take to put charges on there. And in that case, the battery doesn't do anything. It's not that the battery is dead. It's just now the ions aren't moving. There's no chemical reactions going on in the battery. We can't charge it any more than we already have. Now, before I show you this formula, I have it open in another window. I have a really nice thing here. This is from the nice people at FET. Like maybe I can make it full screen. So we've got a battery, and we've got some plates here. So what we can do, we can see the positive end of the battery is up top, 1.5 volts. That's positive voltage. And in fact, all little batteries, AAA, AA, D batteries are common. C, you see once in a while, some things still need C. I don't know why there's no B battery, but there isn't. But there's the A's or AAA's and AA's, but there's no A and B. But it's negative 1.5 down at the bottom. So let's charge it up. We'll just go upward here. So you can see when I'm at 0, there's no charge on the plates. And I charge and charge and charge. But I only have 1.5 volts. There's only so much I can put on that plate. Look at the top of the screen where the capacitance is 0.35 picofarads. Well, let's take the two plates and bring them closer together. You see what happens? As I bring them closer together, the capacitance goes up. As I bring them further apart, the capacitance goes down. So ideally, we want them pretty close together. Let's put them, let's see, we're right about there. That's close enough. 3.5, there we go. Now, what if we had bigger plates? Notice, I can only make them so big on this simulation here. As I make the plates bigger, the capacitance goes up. In fact, it doubled because I went from 200, I think they started out at about 200. If I go up to 400, which is as far as it lets me, I double the capacitance. Smaller ones make the plate half as small, and we really decrease our capacitance. So the bigger the plate, the more the capacitance. The closer we can get them, the better the capacitance. And that's that for that demonstration. Let me tell you one or two more things before we finish the video for today, because this is important too. The electric field. In between the plates is an electric field. Let me draw two plates here. It's always one positive and one negative. You can't have two positive plates and two negative plates. It doesn't work that way. So in between the plates, now let's remind ourselves, electric fields always go from positive and they point away from the positive. Like the positive person away, he gives things away from himself or herself. So in between here, and it's pretty uniform, when you get to the edge of the plates, it kind of bubbles out a little bit, but we're not going to worry about that. Usually you don't worry too much about what are called edge effects, unless you're doing really high-level stuff. There is an electric field, and that electric field is caused by the voltage and the distance. So the greater the distance between the plates, you need a greater voltage to charge it up. And we can see that the voltage and the electric field are directly proportional. As you increase the voltage, you also increase the electric field that's in there. So we're going to need that formula a little bit later on.